Hello and welcome to Elektor Engineering Insights, the show that puts your engineering challenges to the industry's experts. I'm your host, Stuart Cording. While cars for the masses that can drive autonomously are still a few years or maybe even decades away, you'll have noticed that vehicle propulsion systems are changing. Slowly, fossil fuel motorization is making way for electrification. But that is not all that's happening. Software is increasingly differentiating the features and functions vehicles can offer, rather than the hardware. This means new development approaches and electrical architectures within the vehicle, so that new software variants can be distributed and deployed just as we expect from our smartphones. So, how is the industry addressing these changes? To discuss, my panel of experts for this episode are Allan McAuslin from NXP and Felix Martin from iSYSTEM. So welcome to the show, everybody. I'm going to start with Allan. Hi there, Allan. How's it going?
Hi, Stuart. Good afternoon, good morning, wherever we are in the world. Good to see you.
Good to see you. So where are you based and what's your role at NXP?
So I'm based in Glasgow and I'm part of NXP's automotive processing business line. So we own all of the microcontroller, microprocessor, automotive grade components that are ultimately controlling the vehicle dynamics and distribution of power across the vehicle.
Smashing, super. Well, we'll come back to you shortly and dig into a little bit more detail around one of your latest additions to the range for traction inverters in electric vehicles. So hold tight. And we'll just say hello as well to Felix. Welcome, Felix. You're part of the iSYSTEM team. What's your area of expertise in automotive electronics?
Hi, Stuart. Thanks so much for having me. Yeah, so I work for iSYSTEM in Detroit, Michigan. I'm from Germany originally, but I've been here for 5 years, and I'm part of the field application engineering team. So iSYSTEM makes hardware debuggers, and basically what I do is help our customers here in North America to use our tools to potentially find out about new requirements and then feed that information back to R&D in Europe and just like maintain an interface like on the technical side to our customers and also to our R&D in Europe.
Great. Well, thanks very much. We'll come back to you shortly and have a little discussion about how those debugging tools are helping us explore what's going on inside the microcontrollers. See you in a bit. Now, the semiconductor industry gives automotive manufacturers quite a lot of attention, developing dedicated products that continuously optimize vehicle electronics. As internal combustion engines are replaced by electric motors, devices are coming onto the market that address both the application and the quality and reliability demands of the automotive industry. But getting all the different facets of software to work on a piece of silicon is exceptionally challenging, requiring debug tools that essentially enable developers to look inside the microcontroller and see what's going on. Luckily, I've had plenty of opportunities to explore the world of automotive embedded systems. However, this show is for you engineers out there struggling with your challenges. So regardless of where you're watching, post your questions and comments during the show using the chat function on YouTube and LinkedIn, or you can use Twitter together with the hashtag ElektorEI, and we'll do our best to get answers or guide you to resources that might help. Fantastic. Let's move then back to Allan. Hi there, Allan. Welcome to the show.
Thanks for having me.
So what I wanted to start with was a discussion of sort of the basics of what's changing in the vehicle. We've got the new sort of electronic architecture, or EE architecture as it's typically known. And that's changing how the electrical system of inside vehicles is being manufactured. And one of the things we've discussed in the show before is that we're sort of moving away from a function per box to having more sort of boxes of functions. And one approach is that the development of the domain architecture. Could you explain a little bit more about what's changing, the key elements of that, and how that impacts the people developing electronic hardware for cars?
Certainly. So, yes, you're right. So the industry is going through a lot of change right now in terms of how functions are deployed across the EE network in the vehicle. So there's a strong move towards consolidation of functions and very powerful, what you describe as correct, domain controllers. And those, the integration of those functions inside domain controller environments have some obvious benefits, right? So we want to reduce the number of ECUs in the vehicle network, which has some cost and complexity benefit. And we want to remove wiring harnesses where we can, reduce the copper content and take the overall weight of the vehicle, which is going to have an overall benefit in terms of vehicle range, especially for electrified vehicles. But a real strong trend in the market right now is towards software-defined architectures. So every car maker's made an announcement around this language recently, and that's about the car maker really taking control of the overall software deployment in the vehicle. What does that mean? It's about the car maker really owning the energy management across the vehicle, the deployment of torque, and preservation of range, right, for the vehicle. But also importantly, it allows the car maker to build in performance headroom for the deployment of new applications and features through the life of the vehicle. So a lot of car makers now will describe the vehicle that you buy from the lot, right, at the car garage as the worst performing point of its life, right? It's only going to get better, right? The range is only going to improve and extend. The controllability of torque distribution is only going to improve and make the driver experience, ever more compelling. And the car maker wants to own that. So the consolidation of these functions, first of all, has the commercial benefits and the simplification of the EE topology, but also allows the car maker to then say, okay, I'm going to now provide these added functions on top through the life of the vehicle to help make the vehicle more compelling for the driver.
Now, in the vehicle, there's obviously a lot of functionality which can be mostly implemented in software or is primarily implemented in software. The idea of this domain architecture is that software can be sort of distributed to whichever domain controller has spare capacity or has availability to execute that code. But then there's other aspects of automotive, and this has been the case ever since electronics was coming in, is that they require very specialized peripherals on the microcontroller, meaning that you can't just take any microcontroller. You have to have something that has got say dedicated PWMs or ATE converters and the right communication interfaces as well. So for motor control is a good point here, especially now we're moving towards electric traction. And NXP has developed the S32K39, and recently we looked at it at the Electronica show. Could you introduce that product and tell us a little bit more about how it came about and what it's going to be able to implement and deliver inside an EV?
Yeah, certainly. So we spoke there about domain integration, right, which is great for all the reasons I described. But when we're driving motors, you've still got to generate waveforms, right? And you've got to sense analog, sense position, and that's going to have to exist within a very tightly controlled control loop with very low latency, right? So what we've done is we've developed a new family of microcontrollers, the K39, specifically optimized for traction motor control. I do have a couple of pictures that I can share to take you through that. Let me just grab the right picture. So you should be able to see this now. So yeah, K39. So the K39 is a member of our S32K3 family of automotive microcontrollers, all ARM Cortex M7 based, servicing a whole bunch of different automotive applications. This guy here is really, as I said, targeting the motor control application. And we spoke about domain control and the motor control and how all that fits together. I think this is quite a nice picture to explain that the consolidation of functions like power management, like chassis braking, supervisory functions like battery management, state of charge, state of health algorithms, and torque distribution. These are functions that are typically consolidated inside propulsion domain controllers. And these are applications that exist in what we would normally term quite long control loops, right? 10, 20 millisecond control loops, right? Now, if you're driving an IGBT or silicon MOSFET to send current into the phases of a motor, the control loops are typically much tighter, certainly below 1 millisecond. So for that, we have the guy over on the left-hand side, which is our S32K39. Right, so this is a highly optimized High-performing new development, very modern architecture in terms of performance and its ability to handle interrupts and control loops. And that's going straight into that inverter application. Concurrently living together with NXP's gate driver technology, which is ultimately driving the silicon MOSFET, silicon carbide MOSFET, or IGBT MOSFET, which is pumping current into the phases of the motor. And as we're moving now to ever high switching frequencies, physically smaller motors, but with a high power output, the industry is moving towards silicon carbide. Silicon carbide brings some benefits in terms of switching losses, but silicon carbide requires switching frequencies that are typically much higher than IGBT. So our K39 is designed to handle very high switching frequencies, very high frequency control loops for that traction motor application. And in fact, we can handle 6 phases, or in other words, two motors, 2 3-phase motors, which is a kind of typically deployed topology by the vehicle manufacturers these days, especially for the high performance systems. You're going to have 2 motors on 1 axle typically. Our K39 is designed to handle that. In addition, for some motors, you have a secondary drive component, maybe a rear axle traction motor. And for that, we've also got our domain controller application processor, which can physically drive that rear axle motor, in addition to hosting the multiple ECU integration tasks. So that's what the K39 is for, right? How it looks. Well, here's a block diagram, and don't worry, Stuart, I know we're tight on time. I won't go through all of this. Let me just explain very quickly what it does and what it's there for. So we have the ARM Cortex M7 platform, and this is a fully loaded ARM Cortex M7 from a performance point of view, 320 megahertz operation, fully loaded with tightly coupled memory and cache, instruction and data cache to drive as much performance as possible. So we have 3 logical cores on here, 2 decoupled cores, and 1 lockstep pair of cores to give you three logical cores in total. And what we'll typically do here is we'll run our FOC, our motor management application, up here on one of these M7s. We'll be sensing analog thanks to our Sigma Delta or successive approximation ADCs, and we'll be generating waveforms with very high resolution PWMs, which are allowing that very high switching frequency that's required for silicon carbide silicon machines. So that's what it's there for. That's what it does. Up to 6 megabytes of flash, a very wide array of analog sensing components, a very diverse set of IPs for motor control. We have dedicated motor control acceleration engines. We call them motor control coprocessors. We have high resolution PWMs with general purpose timers. And really the architecture has been put together to be optimized for that, those very tight control loops that are required for new generation electric motors.
Now, when I was at the Electronica exhibition, I was talking to your colleague Brian Carlson, and he kindly gave me an overview of the demo, which I took a video of, and I was just hoping that if I pull up the video, you might just take us through some of the features that we see in here.
Certainly. So this is a motor control board featuring the K39 silicon. And here you have also the power management IC coming from NXP, the FS26. There's our K39, and we're also connecting this EVB to a power stage driver, so the GD3162 gate driver, which is a new development from NXP, from my colleagues on the analog side, highly optimized for the fast, high voltage gradients required by silicon carbide machines, especially for acceleration of heavy duty vehicles. And here what you see is our tuning tool. That's our motor control tuning tool, which NXP provides. So NXP provide motor control libraries, a model-based design environment in order to develop motor control algorithms. We're also providing the back end of that, which is the motor control tuning tool, to ensure that you're getting the respective performance that you require out of that application. Yeah, so we're happy to announce that at the show, and with plenty of visitors. And I know my colleague Brian and a few others were very busy demoing that to various different companies.
So obviously, in the past, the automotive industry has been very big on promoting the performance of the engine. You know, how many cylinders, what's the horsepower, 0 to 60 measurements and things like that. And of course, that's all been taken away from fossil fuel burning motors, and it's going into the electric motors. And they were very protective of all that information. Sort of that was their core USP and their differentiation against their competitors. I guess it's similar for, you know, the use of electric motors, but can you give us some idea of what sort of electric motors we're talking about being used in these vehicles, and you know, what sort of, how they're different from maybe sort of three-phase motors we may have seen in other smaller applications like industrial applications?
Yeah, well, I mean, if you think about it, you want to drive a lot of torque, right? So it's that means high current and high density output, right? So permanent magnet motors are most typically used today. So most of the designs that are launching right now are launching around permanent magnet architectures. But permanent magnets use rare earth materials, which can sometimes have a kind of volatile supply chain, and are sometimes you know, subject to volatile pricing, which, you know, car makers don't like. So there's a lot of investment right now around new flux-based motor technologies. Axial flux is a really interesting technology. Here you have the magnetic drive is in parallel to the axis of the motor. So the motor design, the physical motor design, can actually be much smaller, while guaranteeing, you know, equivalent or even higher output when compared to permanent magnet. So we start to see some of those axial flux motors appear right in the middle of this decade. I know Renault have announced a partnership with a motor vendor for that. Yeah, so and then electrically excited motor technology also coming to slightly different electrical behaviour. But the point is, from a control point of view, we don't really care, right? Because we're building architectures that have the control horsepower in order to drive very high switching frequencies with very low latency control loops, sensing motor position, deploying high resolution PWM to control those motors and ultimately deliver torque in a clean and efficient way, right? Minimize switching losses, you know, minimize lagging in terms of applying torque to the axle. And this is ultimately going to preserve the range of the battery, which is the most, you know, prized commodity for the consumer.
Now, most of the motors, I understand, are three-phase motors, but there are, I understand, also applications that are using six-phase motors when you've got very heavy usage, for example, like taxis. Is that the case?
Yeah, so six-phase motors are coming along. There's a couple of different benefits, if you like, to six-phase. First of all, more high fidelity control of the distribution of torque to that motor, right? With 6 phases, you have you know, twice the application of torque. One other key value is for safety, right? So if one of the phases in the motor goes down, then ultimately you can turn that six-phase motor into a three-phase motor, right? And then you still have the fundamental basic, you know, capability to drive the vehicle. You mentioned taxis. Yes, some heavier duty vehicles are deploying six-phase. The issue is cost, right? So for mass market city car, I don't see it for a long time unless the motor, the cost of that physical motor really comes down in price. But for the heavy duty machines, yeah, it's probably going to start to grow towards the end of the decade.
And I think I was surprised when I first started exploring how the electrical drivetrain was being implemented, that, you know, we're still going for a motor, a gearbox, and then the drive to the wheels, and sort of hub motors don't really seem to have taken off in any big way. Is that also what you're seeing? Is the hub motors just too expensive or too difficult to guarantee the reliability over the lifetime of a vehicle?
It's early days for the hub motors. You've got a distribution of control problem too, right? So the software is eventually distributed. So you're implementing torque vectoring, torque control algorithms from something like a domain controller, and then each of those four corners of the vehicle have got to be synchronized in terms of how they're deploying torque. So it's not an impossible thing. It's just it takes time for the car makers to prove that out, get the hundreds of thousands of road miles in the bank, and prove that the technology is viable. There are proof of concepts right now. We're working closely with a few customers, a few car makers on in-wheel architectures. They're really exciting because in addition to the in-wheel traction motor, you also have the possibility to integrate adaptive suspension, braking, other functions that maybe exist in that corner of the vehicle. You can also co-locate to that processor. So watch this space. It's definitely coming.
Now, efficiency is also key, and you've already touched on that in your discussion of the motors, and also one of the things we're seeing from the power industry, power supply manufacturers, is this move to wide band gap. Is the S32K39 ready? I think you already mentioned that it is ready for SiC and GaN, but what's sort of holding back the move from IGBT to wide band gap, and is GaN going to play a role in these types of applications, do you think?
So definitely building the silicon vendor capacity for silicon carbide is taking a little bit of time, but we're closing that gap. And by the way, NXP are not a silicon carbide silicon provider. It's other companies who do that. But yes, we're closing that gap from a supply point of view and a capacity point of view. There are some electromagnetic considerations that need to be taken into account, especially around about the gate driver protection, which will take some time to iron out, but we'll get there. And then I think very quickly you'll see a move to gallium nitride. Gallium nitride is capable to switch at extremely high frequencies, right beyond 200 kilohertz. Which can again drive the switching losses even lower, right, and help extend range, and can also help drive, on the other side, smaller motor densities, right? So we'll see some gallium nitride proof of concept or luxury premium vehicles on the road in a few years. And then what comes after that's gallium oxide, where we're switching even faster with even less on the switching loss side. So there's going to be a long and continual evolution.
And what's the challenge then for the algorithm developers and the hardware developers then as they're moving to these different switching devices?
So I guess the electric motor is the biggest offender on the electrical network, right, for losses and loss of energy, right? So there's two things that help solve that. It's move to more efficient MOSFET technology, which we've spoken about. The second is improved control algorithms. Right, control algorithms that are capable to adjust to very rapid acceleration on a heavy vehicle and to ensure that current is not lost and eventually energy is lost and the battery becomes drained. So what that requires is pretty high performing and very low latency control loop, right? So what does that mean? It's a closed loop system. You've got to sense the position of the motor. You feed that position of the motor into an FOC, a field-oriented motor control algorithm. You determine then the torque that you want to distribute to that motor through the application of a very smooth waveform. Now, what we take care of on NXP's side is the capture of the motor position, right? So determining the motor position, we generate the waveform, but then the key part that the car maker or the tier one supplier can bring is the very highly optimized algorithm, right, for that motor control. And that's where the secret sauce is. So we provide reference software, motor control libraries to help them put that stuff together. But what they often have on top of that are some very special bespoke motor control, at the atomic level motor control algorithms that they can deploy. Now, on our S32K39 device, we've got plenty of headroom for those customers to deploy their secret sauce. In addition to that, what we can also allow is the application of features like Observer. right? So an observer is a model of the motor that runs in conjunction with the real-time motor control, constantly monitoring whether or not the motor is behaving as it should do, right? So that's another key value that NXP solution can bring. So NXP provide all of the model-based design toolkit to develop that observer and monitor the motor. Yeah, so these are the values that the car makers can bring, and we can certainly help enable that.
How does it look on the analog side? I guess that the IGBTs or SiC MOSFETs, there's a certain amount of monitoring through A to D converters maybe to keep track of what's going on, make sure there's no overheating, immediately respond to sort of short circuit conditions.
Yes, so we're in quite a good position at NXP because we've got gate driver technology, we've got the microcontroller technology. We also have power management technology, and this allows us to put together kind of system level solutions, right, with functional safety concepts that can help the customer to deploy these monitoring applications cohesively across a number of different components, right? So that because we're in this position where we supply mostly everything except the MOSFET, all of the control, certainly all of the control NXP are providing, we can put together some recommendations, some design guides, we call it safety application guide, and we can provide that to the car maker, and that gives them a running start for deployment of voltage monitoring, over voltage protection circuits, voltage tracking circuits, and we can help enable them with that.
Now, an important aspect of those field-oriented control motor algorithms is obviously understanding the position of the rotor at any one time. And when we look at various applications on the market, there's often a big focus on sensorless control, because obviously it reduces the cost of the motor. It's one less thing to go wrong. What's happening in the automotive space? Is it a sensorless type motor control application, or is there some sort of sensor, and how is that information then passed back to the microcontroller?
Sensorless, there's a lot of development right now on sensorless. It's not quite ready, I don't think, in my opinion. But what it will drive is a hell of a lot more compute, right? To resolve those sensorless inputs on the microcontroller. I think we've got the headroom to accommodate that. What's more common these days, there's typically a hardware analog component that exists on the traction motor PCB. It's called a resolver, right? And that feeds input via an op-amp back from the motor to determine the angular position of the motor. And that's a physical component on the PCB that determines that position. That's an expensive component, so we try to help the customer remove that from the PCB. We have a software resolver that we deploy on our silicon. It's provided by NXP. It's an application, automotive grade application that NXP provide free of charge, integrated into the chip price actually. You don't get it free of charge unless you purchase the chip. But that runs on our coprocessor, on our timed I/O coprocessor. So therefore you can determine the motor position without spending the bill of materials money on additional components. And I think that's the trend right now. The trend right now is to move away from hardware motor position sensing to software sensing.
Right. Now, one of the other aspects of the software-defined vehicle, as you rightly highlighted at the beginning of the discussion, was this ability to update the software over the lifetime of the car. But one of the ongoing challenges that keeps coming back to, you see lots of hackers showing off their ability to break into a vehicle and control it remotely. So how are we going to make sure that the firmware in the traction inverter is safe, is over-the-air updates are secure? Is the intention that there's a domain controller which takes responsibility for all the security and defines who gets what and when, or is there security built into a device like the K39?
Well, there's a few different ways to skin that cat, right? So our approach is to cover every eventuality ultimately, right? So within the S32K family of microcontrollers, we have fully Evita compliant and beyond Evita compliant hardware security engine, right? HSE, and this is really like a microcontroller within a microcontroller. right? Now, the reason why this is important, it's not a solid state machine, it's not a fixed function piece of IP, it's a programmable machine, and it's programmable via firmware. So what NXP will provide, and straight off the bat, is full support for symmetric, asymmetric encryption, elliptical curve support. We'll do custom keys, because certain car makers like to have their own set of encryption keys for their application. We'll do all that, right? But because this is an engine, it's firmware upgradable in the field, right? And because NXP own that IP and we own the firmware, and we have close engagements with all of the car makers around the world on their specific key requirements, we will continue through the life of the vehicle to update and provide firmware updates for OTA and security updates. So that's how we mitigate against those security threats, but those security threats are never going to go away, right? So we need to continually increment our cybersecurity awareness and respond to those in real time, right, in order to make sure that those OTA updates are constantly being deployed on the vehicles and in the field.
Well, thanks ever so much for those insights. I've got lots more questions, but we're running out of time at this point, and I'd like to obviously get on to Felix as well and look at some of the debug side. So stay with us there, and we'll catch up with you at the end and have a discussion in the round.
Okay, thanks.
Thanks very much. So to thank you also for supporting the show, we offer our viewers the chance to participate in a giveaway. In the last episode, Ivan won an ESP32 Smart Kit bundle, and this time it could be you. My giveaway this time is a copy of The Art of Electronics, and as I mentioned that, of course, I'd like to show it to you. So I'm just going to pull that up here as well. There we go. That's The Art of Electronics and the link to participate in this giveaway. Now, The Art of Electronics has been variously described as an epic work, spectacular, deep and wide, and this is a good one in the Amazon reviews I took a look at today. This third edition continues excuse me, so excited. This third edition continues where previous editions left off, collating extensive practical advice and back-of-the-envelope techniques in its 1,200 pages. Written by Paul Horowitz and Winfield Hill, it truly is the must-have book for every electronics engineer. If you'd like to participate, use the link at the bottom of the screen and enter the code word Horowitz, that's the code word Horowitz, with your entry. And I wish you all the best. Now we're going to move on to Felix from iSYSTEM. Hi there, Felix. Let's bring you back in.
Hi, Stuart.
Space for you here on the screen. So I'd like to start at the beginning. Now, when we're developing with any sort of microcontroller, most of the industry is fitted with some sort of ARM Cortex MCU, and a standard USB-based debugging chip is on there to allow developers just to get starting with the semiconductor manufacturer's IDE generally. Now, how do these tiny little microcontrollers support basic debugging and programming of that microcontroller?
Yeah, so if we really want to start with the history, then the history starts like way before I was born. So excuse me if I make any mistakes explaining it, but initially microcontrollers did not have a built-in way to support debugging. So at some point, as you mentioned initially, people realized, okay, when we develop software for these microcontrollers, we need a way to debug them, to first Flash to download the code, and then to run the applications, maybe set breakpoints, look at variables, and so on. So historically, the first solution for that was what's called in-circuit emulation. So there are different ways of doing that, but usually it involves removing the actual microcontroller and then replace it with a different set of hardware that then emulates that microcontroller and has additional capabilities either in software or in hardware that allows an external tool to access the internals of the microcontroller. So again, that can either be done, in the past it was done via like bond out boards. So basically the chip internals, like the buses, were made available to external hardware via dedicated pins. And then a little bit later, that was then maybe done in software where you had like a superset device that runs additional code that features a protocol that allows a debugger to connect with that software, and that then the software would take care of like running, stopping, reading out variables, and so on. So that's all super tedious and not as convenient and easy as you described it, like how it works now on these ARM boards that you can get everywhere at every show. So nowadays, the debugging is not an afterthought, but something that the semiconductor vendors obviously are aware of, that their customers need to do it. So if you maybe want to share my first slide, then
Yeah.
you can see how it's done nowadays. Because today, what we see here is like the gray block in the middle. That's actually a block diagram for S32K3 that we discussed before. And so the part in the middle where we see the Cortex M7 core, that's the actual business logic. And then on the bottom, we have like the orange box peripherals. That's like all the other blocks that we saw earlier on the screenshot or on that block diagram that Allan showed. But the point here is we also have the green blocks and the orange blocks. So the green blocks is, that's like the on-chip debug logic. So what the semiconductor vendors do is they put dedicated units onto the silicon that interface with the outside world via dedicated pins. Usually the protocol, or historically the protocol, is JTAG, although nowadays there are different protocols that maybe use the same pins, but a different protocol for better data rates and other features. We can talk about that in the ARM world. Like an alternative to JTAG is called SWD. And so via this on-chip debug logic, external tools now have to have a way to access the microcontroller without any need for in-circuit emulation. So now if you get like that board from the show that already, like where you can just connect via USB, the way that it works is you have the microcontroller, and then you have an additional little chip on the microcontroller board that interface with that debug interface, and on the one side, and interfaces to like micro USB, for example, on the other side. And that way you can open your debug GUI on your host computer. It connects to that chip. There are different solutions for that by different vendors, but it all works the same. So it connects to the chip, and then that chip actually connects to the microcontroller via the dedicated debug interface, either via JTAG or via SWD in the ARM world.
It's funny that you went back to the original history of the in-circuit emulators, because when I started working with our joint acquaintance Wolfgang Höld at National Semiconductor, he gave me this huge in-circuit emulator. It was about 10 boards all stacked on top of each other to slot into a little 100-pin LQFP socket, and it was absolutely enormous. But like you say, the only way of really debugging the devices in any meaningful way. And I think that's the interesting point that you raised there. I think most people who've got those boards from a trade show, they've plugged it into the USB ports, opened up an IDE, and immediately you have some basic debugging capability. You can download code, you can execute the code, you can halt and step through lines of code, or even at assembly level, and you can also examine the memory contents. But when we get into automotive applications and other complex applications, that's not really enough, is it? We need sort of more advanced debugging features. So how is things like trace and that implemented, and what does that deliver the development team?
Mm-hmm. Yeah, good question. So the blocks that I haven't mentioned on this diagram yet are the orange ones. So we have the ETM, the embedded trace macro cell, the DWT, the data watch and trace unit, and the ITM, instrumentation trace macro cell. Yeah, a lot of abbreviations. But basically what these blocks do is they provide trace capabilities. So the way that debugging works is, well, usually you do run and stop debugging. So you set a breakpoint at a certain location that you're interested in. The microcontroller stops. Your GUI shows you where you are in the source code on C level and also on assembly level maybe. And then you single step through the code to figure out what your application is doing. Now, especially in environments like that we talked about, like engine control systems, it might not always be feasible to start and stop the microcontroller. You might have some external hardware dependency that will not react well to simply bringing the microcontroller to a full stop. So in such scenarios, trace can be really helpful. So what this on-chip trace logic does, like these orange blocks, they are able to monitor what the microcontroller is doing, but without influencing the runtime behavior. So you can basically think of it as a part on the silicon that only monitors what the chip is doing without influencing the runtime behavior. And what that then allows you to do is it allows you to record program flow information. So basically what the microcontroller, the CPUs are doing, and also data information. So for example, if you are interested in accesses to certain variables, it can, because it can monitor everything, it can monitor this and record this information and then send it out via the debug interface. So on the block diagram, that would be kind of the top right corner here. And for tracing, there are different interfaces available. So you can do it via the standard debug interface. If you use this SWD, the serial wire debug, then ARM provides a single pin trace output interface. So I think it's actually called that, single wire output trace. And so you can use that to send trace data off chip. And then beyond that, if you want to record more information, they actually dedicated trace interfaces. And at that point, usually you will run out of luck with your little demo board, and you will need a dedicated way to access these, like either it's a parallel trace interface, or it can be a high-speed serial trace interface. There are different IPs. So you need like a dedicated tool to access, to connect to that interface, and then stream all that trace data off chip. So for example, if you want to really observe the complete application, the full program flow of on a single CPU core, then you need like a high-speed interface like that. And once you're doing that, then you get full insight into the runtime behavior. So your application just runs, and if you know in certain situations like an error occurs, maybe you have like a variable or a flag that indicates that something is going wrong, you can like trigger on that particular event, like on your application going into the error state, and you can see like what your application was really doing before that error condition, and then hopefully find the bug or the issue and resolve it.
So trace is giving us a lot deeper insight into what's going on. We're seeing the program execution, and we've got an ability to access the data memory. Just a sort of a quick clarification on the program trace. Are we able to, especially in this device that we're talking about here, we've got 3 cores all running in parallel. Can we trace all the program code, or are there limits, and we have to sort of selectively decide which parts we want to trace?
Yeah, good question. So even if we, let's say we have a high-speed serial interface, usually we won't be able to record like the full program flow trace on all CPU cores. It's just too much data that is being generated. And even the program flow does not even record like every single value of the program counter. It uses some like compression algorithms, and then the debug hardware like reconstructs the full program flow trace from that information. But even that compressed program flow trace, it's just like too much data. So what these on-chip logics provide, like the ETM, for example, you can limit down the amount of trace data that you want to collect. So either you limit the program flow trace on certain memory areas, or you trigger on specific events. So you say, okay, only when a task with a certain ID is running, I actually want to record program flow trace. And that way your data generation rate gets decreased, and you are able to record again without overflowing any of the on-chip trace buffer.
Now I can imagine that that's all well and good to be able to trace the program code and see what's going on, but there's also so much other information that's being passed around these sort of systems. And I'm talking about motor control in vehicles. We've obviously got digital and analog signals, and then there's data communication over CAN. Is it possible to also capture what's going on around the microcontroller at the same time as what's going on inside it?
Yeah, so we at iSYSTEM, in addition to the hardware debuggers, we also provide so-called add-on modules that you can connect to the debugger. And we actually have one for CAN and LIN network communication, and we also have one for digital and analog I/O. So what that allows you to do is, and maybe if you switch to the next slide, it gives a little bit a better representation of how like such an analysis might look like. But basically what these additional modules allow you to do is you can correlate the on-chip trace with the data, with the information, with the messages that are sent on the CAN bus, for example, or you can correlate the on-chip trace data with a certain analog signal, for example. And that's what's shown on this screenshot. So we have OS threads and runnables. So the dark red indicates that a specific object is running. So we have the x-axis is basically the time. And so you can see different objects are running over time. And then the bottom, there's also like two lines where like there's like an actual CAN message recorded on the bus. And then what that allows us to do, we can follow the data flows through the whole system basically. So we can see, a certain CAN messages on the bus that the triggers CAN interrupt, and then that CAN interrupt via the operating system runs a specific runnable. So we can really analyze the system as a whole. So yeah, the CAN bus, different I/O information, and also the application itself via trace.
So we're running quickly through our time. To say it's such a fascinating topic that the time just disappears. So one thing I was wondering here then is we would also been discussing the fact that we've got software-defined vehicles. That's the future of the automotive industry. And in the past, at least my experience was that the companies, they developed the software for a parking brake ECU, and when that was finished, everyone left it behind and they moved on to the next thing, and that was never going to be touched again unless there was a product recall. How are we going to sort of create a more agile way of software development, and are the debug tools part of there to support things like continuous integration as well?
Yeah, totally. So we definitely envision and encourage our customers to like also use our tools in a continuous integration environment, because as we've talked about, like the debugger gives you full access to whatever the microcontroller is doing, so you can utilize that to run unit tests, but also run system tests, and you can go all the way up to integration tests. So like a typical setup would be where you have a continuous integration pipeline where you have nightly builds, and then after the build has finished, it will actually use a debugger. So the iSYSTEM debugger provides an API, so it can use the build server basically can use that API to flash the target and then run different tests on different levels of abstraction. So for example, you can run unit tests. Basically, if you do that, the debugger sets up the program counter, the stack, initializes the stack, and then runs the application, then reads out the return value at the end. So you can test on that level. But you can also think about integration tests where you just flash and then run the application, and then maybe check if the application is running okay by observing the CAN bus. But yeah, you can definitely do that in a continuous way. And that way, every night you get confirmation that your application still is running as it's supposed to be, and wasn't broken by any changes to the code.
Well, thanks for giving us that overview of the debug environment within these microcontrollers and how debug tools support the development of code around them. I'm going to bring Allan back into the discussion, and let's have a quick chat about some of the joint situations we find ourselves in developing these applications. I think Alan's still got his mic turned off at the minute.
Sorry.
There we go. Super. So there we are. Yeah. So I mean, Alan, how much use is the sort of trace analysis in the development of motor control algorithms when you and your team are working with customers?
Massively, right? So I mean, I'm not in my office today, but in my office we've got all of that stuff, distributed around the place. This is really about. I mean, I spoke earlier on about the need for extreme control of waveforms, right, and the reduction of latencies, right. So tools like this are absolutely key to squeezing the application. So first of all, you get the application to demo level, right. You show that you can generate waveforms. Then you've got to make it production quality, and these tools are absolutely critical for that step.
And Felix, we were talking about the performance of the K39, and there are other automotive microcontrollers on the market which are sort of equally high performance. They're operating at hundreds of megahertz. They're multi-core. How on earth are people sort of searching through these trace data? What sort of features are sort of built into the development tools that you offer in order that you can even find where an issue may have occurred?
Yeah, I mean, you need some way to detect where even like some error condition, right? Like I talked earlier about, like, maybe there's a certain like trap that you land in, or maybe there's a certain variable or a certain flag that is set and indicates like if an error condition has happened. So what the tool provides is, like, it provides you with different triggers. Like, you can look for specific values of the program counter, or you can trigger on certain values for a specific memory location, and then that is kind of like here at this point, this thing happened that you didn't want to happen, and now we can show you what happened before that point, and that way you can you don't have to search through, like, let's say, minutes of recording. You can just focus in on the point where the actual issue occurred, and then go from there. So that's maybe the way that customers usually approach this challenge.
Great. I'm just going to turn to our audience. We've had a few people online watching us today. Just a quick shout out to the MGT group who I met at Electronica the other week. They're also big in wide bandgap technology, so maybe there's some nice SiC MOSFETs available there for automotive applications. And also to Nicholas Stefanovic, who's joining us as well. So thank you for joining today to the live stream and participating. Another question also was in terms of the continuous integration, continuous deployment aspect of things. Felix, what sort of software are people using? Is Jenkins is quite popular for the development of code in other industries. Is that something that the automotive industry is using, or do they have sort of dedicated platforms or self-developed platforms for that?
Yeah, actually, so Jenkins is like becomes more and more widely used, but a lot of the software that we use is actually some kind of like in-house continuous integration frameworks that have been maintained over many years, and then like that glue together all the different tools. So yeah, there are like some, let's say, mainstream professional environments used, but there's also like a lot of in-house software. I don't know, maybe surprisingly. But on the other hand, if you have ever played around with Jenkins and set it up, it's also not that easy to handle. So maybe it's not that big of a difference to maybe you need in-house development one way or the other. So yeah.
Yeah, choose the not so worse software, basically. And Alan, in the traction inverter space, the K39 is capable of driving 2 3-phase motors. Do you see sort of a process of maybe optimization or development for that family in the coming years? What are the automotive industry asking you to put in for sort of next generation devices?
So you spoke there about CI/CD. So what ultimately we're helping the car maker to deliver is a virtual model of the microcontroller, and then he uses that virtual model to deploy that in his virtual level ECU, and eventually he wants to have a digital twin of the vehicle. So from end nodes like traction motors, even body control nodes, battery management nodes, right through to domain-based applications, zonal integration, right, gateway functions and services. This is a new requirement that's being bestowed upon us, is to go and develop virtual development environments to allow that CI/CD to occur during the development phase, but also to continue through the life of that vehicle on the road, right? So we can then test, regression test, and then deploy new software functions.
And when customers are developing these applications, I mean, it's very easy to sit down, say, someone who's using an Arduino or a Raspberry Pi, you sit down, you write your code in C, and you execute it, and it runs. And in the automotive industry, how much of it is still handwritten C and hand optimized assembler, and how much is moving into the world of model-based design?
Oh, it's a slow transition, I would say, right? So most vehicles right now are out there on C or even hand optimized, assembly or SIMD DSP code. Yeah. For things like traction motor, yes, there's a move now in the next few years. I think as the car makers are starting to take control of software from the supply chain, they are taking that step, and with that step, deploying model-based design techniques. Right, so a key fundamental requirement when we develop a new microcontroller is we provide model-based design tool enablement in order to abstract from the hardware and allow that developer to build MATLAB Simulink models. So it's kind of slowly coming, right? And it's coming for control-based applications faster than it is for super integrated cross-domain applications. So something like inverters is a good candidate for that model-based design.
Felix, the key sort of, let's say the operating system framework is AUTOSAR, and then we also have AUTOSAR Adaptive, which is sort of more capable of supporting Linux and I think virtualization. Are you seeing that is also still going to have some life in it for the next few years, or for software-defined vehicles and the complexity of this sort of a system of systems that we're going to get in the car? Are the automotive manufacturers saying, hey, we need to rethink this in the same way as like Tesla's just started with a clean sheet?
I mean, I would say, like, for AUTOSAR Classic, it's not gonna go away anytime soon, because like some of the, I mean, I know we talk about centralization and so on, but like the dedicated microcontrollers for like very specific domains, like they will continue to be safety critical real-time microcontrollers, and I think they will continue to use AUTOSAR. And then when it comes to AUTOSAR Adaptive, like, so when we talk about these like centralized computers, you can already almost say, then I'm honestly not so sure. Probably Elektrobit and Vector have like better insights at this point. We don't see adaptive that much yet. It's more, like you said, like more like a West Coast mindset where we just like run a Linux maybe with some real-time patches and build something together like that. I like, at least from what I've seen, AUTOSAR Adaptive is not widely spread yet, maybe in that sense, but probably Elektrobit and Vector, like those vendors would have more insights to that question.
Yeah. Great. Well, I'd like to thank you both for your contribution to the insights that we shared with our audience today. It's been great talking to you, and thanks very much for your time, and we look forward to finding out more about what's going on in automotive electronics and software-defined vehicles in the future from you both.
Great. Thanks for having us, Stuart.
Thanks so much, Stuart. It was a lot of fun.
So the automotive industry has reached a fascinating point in its history. Software is starting to define what a vehicle is and what it can do. But due to the safety and reliability demands, coupled with the need for software upgradability in the field, how the electronics for these systems are developed is changing. Cars are exceptionally complex distributed systems, a system of systems if you like, offering challenges from high-performance computing through to classical embedded systems development. Semiconductors are truly innovating to deliver microcontrollers that integrate advanced capabilities to meet the needs of cars and trucks. In parallel, development tool providers ensure that these systems can be developed and tested despite the enormity of that challenge and for the lifetime of the vehicle. Thanks go to my experts, Allan McAuslin from NXP and Felix Martin from iSYSTEM. You've delivered us with some brilliant engineering insights. So that wraps it up for today and this year. I hope you've enjoyed Elektor Engineering Insights as much as I have had producing it. Thanks to your interest and support, we've decided to bring you engineering insights fortnightly in 2023, rather than just once a month. We'll also be filling the gaps in between with news bites from the industry, keeping you updated on interesting semiconductors, electronic components and developments in the field of test and measurement. And to make all this easier to find, we've created a new YouTube channel, Elektor TV Industry. So don't forget to search it out and subscribe. Now the schedule for the 2023 shows will be updated soon, so drop by the website at elektormagazine.com/Elektor Engineering Insights to see the topics for future shows. And if you'd like to join me as a guest, write me an email, drop me a tweet or reach out to me, Stuart Cording, on LinkedIn. Thanks for joining, stay in touch and don't forget to keep asking your engineering questions.